Hi students, welcome again. Today we will continue the topic projectile motion, but this time it will be on an inclined plane. So let us see what changes are to be made and how you can solve questions based on this. The topic is more important for students who are preparing for JEE. So let us see this. Here comes projectile motion again, but with different aspect. This time we are going to analyze projectile motion on an inclined plane. In previous section it was on horizontal plane and now this is on inclined plane. So let us first draw the condition. If a projectile is thrown from here on an inclined plane, let this inclination be alpha and it is thrown at some angle beta to the plane. This time, to make our analysis easier, we will consider this plane itself as x-axis and of course perpendicular to this as y-axis. And let us see how different aspects of motion can be represented. This is the initial velocity u. Now as we can see, along the incline, if we are writing initial velocity, what it would be? That is ux. So ux can be written as u cos beta, as the projectile is making angle beta with x-axis. Here our x-axis is along the incline, so this component will be u cos beta. And what about acceleration? Acceleration along x-axis will be, now we know that acceleration always is in vertically downward direction. So if this angle is alpha here, let us draw a perpendicular. This also would be alpha. And so g along the perpendicular direction, that is along the y direction, can be written as g cos alpha. So along x direction it will be minus g sin alpha, which is along negative of the x-axis. Similarly along y direction I can write uy is equal to u sin beta and ay is equal to minus g cos alpha. Here motion is not that simple as in motion on a horizontal plane, because in horizontal plane for projectile motion, x direction of motion was a uniform motion where no acceleration was acting, because acceleration was in vertical direction, so its horizontal component was 0. In x direction we used to write as equation for uniform motion. Only in y direction acceleration was effective. In case of this projectile motion on inclined plane, now acceleration is effective both in x as well as y direction. So here we have to consider in both the direction acceleration, which is expressed here as ax and ay. And in both the axes, along x-axis and in y-axis, the motion can be written as uniformly accelerated motion. Now let us write equation along x-axis. What it would be? Equation, we know that equation of motion is v is equal to u plus at, s is equal to ut plus half at square. So if we write these two equations along x-axis, it can be written as vx is equal to ux plus axt. And what is ux? That is u cos beta. So it is u cos beta minus g sin alpha t. Similarly, displacement in x direction can be written as, I am writing ut plus half at square. So that is uxt plus half axt square, which can be written as u cos beta t minus half g sin alpha t square. These are the equations along x-axis. Along y-axis will be vy, that is uy plus ayt, which can be written as u sin beta minus g cos alpha t. And displacement along y-axis is uyt plus half ayt square, that is equal to u sin beta t minus half g cos alpha t square. So we got all the relations which is required to analyze motion of a projectile motion, the velocity relation and the displacement relation. Now let us come to derive some very important terminology which is needed for writing equations of projectile motion. The first one is time of flight. These are very handy formulas which can be used directly in our question if a situation arises. So let us see what is time of flight. Now here, as you can see, this is motion along an inclined plane. So if we take time of flight as capital T, then what about the displacement in the whole journey, that is the time spent T? What it would be? It had started from here and landed again on the same level on x-axis. So since initial and final position are lying on x-axis, so y displacement for this entire journey we can write as 0. And I am writing here the y displacement, that is delta y is equal to uyt plus half ayt square, where t can be taken as time of flight. So if t is time of flight, then delta y reduces to 0. And we got 0 is equal to uyt. Now uyt is u sin beta t. This time I am denoting the time of flight as capital T minus half ay, as we know, is minus g cos alpha. So minus half g cos alpha t square. On solving, t will come out as 2u sin beta upon g cos alpha. Can you compare this relation with the relation we had got in simple projectile motion where it was on a horizontal plane? Of course it can be, because the term this u sin beta is uy. So it can be written as 2uy upon gy. If you now compare this result, in that projectile motion also we had got t is equal to 2u sin theta by g, which was 2uy upon gy. The only difference is that in that kind of motion, y-axis was along vertical and now it is perpendicular to the inclined plane. Next one comes range along the incline. In similar fashion, we are going to derive range along incline as well. If this is the range, here angles are given alpha and beta, perpendicular axis being y-axis, and this is projection velocity u. Now for range, as you know, motion is taking along x direction. So it can be written as delta x, that is equal to uxt, and this t should be time of flight because we are deriving range for the whole journey. So it has to be time of flight here. Uxt plus half axt square. Already we have value of t derived, so directly that can be used, and range can be written as, what is ux now? U cos beta. So this is u cos beta t, and t now we can use from the previous result, which was 2u sin beta upon g cos alpha. So it can be written as 2u sin beta upon g cos alpha minus half ax is g sin alpha and square of t, which is 2u sin beta upon g cos alpha, square of this whole. If we solve it, finally the result will come as 2u square sin beta cos alpha plus beta, and this whole divided by g cos square alpha. So this is the formula for range along x-axis. It is not the horizontal range. Here horizontal range won't be equal to range along x-axis. So this is the range along x-axis. Now if in some question it asks for horizontal range, then in similar fashion we have to write equation along horizontal direction. Not along the x-axis, it has to be along the horizontal direction. That we will see later in some of the question. The next is the condition for maximum range. As we have just now derived the formula for range, so let us see what condition could be there if this range has to be maximum. Now since here r depends on angle of projection, that is beta, it is the only variable. R is some function of beta, which is the only variable involved here, because alpha is angle of inclination which has to be fixed, initial velocity g all being fixed for a given condition. So only beta can be changed, and we can say that r is a function of beta. So if r has to be maximum, then dr by d beta should be 0. And what we have to do? We have to differentiate this expression we got for r with respect to beta and then equate it to 0. So let us first differentiate this. dr by d beta would come as 2u square upon g cos square alpha. These are the terms which are independent of beta. So I am writing it before the differentiation. And then d by d beta of cos alpha plus beta into sin beta. Here I have separated the expression in two parts. First part is independent of beta and second part is dependent on beta, which is to be differentiated. This will come as 2u square upon g cos square alpha cos alpha plus 2 beta, which has to be equal to 0. What this mean? Because the first term cannot be equal to 0, which is 2u square by g cos square alpha. So for this entire expression to be equal to 0, this term has to be 0, which is cos alpha plus 2 beta. And the general solution would be alpha plus 2 beta is equal to pi by 2. As we know that cos pi by 2 is 0, so it has to be equal to pi by 2. From here we got beta is equal to pi by 4 minus alpha by 2. So this is the condition required if range along x-axis has to be maximum. Directly it can be remembered and used whenever required. Now we got the condition for range to be maximum. And what is this maximum range? So if we substitute the value of beta we got in earlier expression and for r, then we would get the maximum range. So now r maximum can be written as r maximum will be when beta is equal to pi by 4 minus alpha by 2. Now I am going to substitute this value of beta for maximum range. But then two cases has to be considered. The first case is when projectile is thrown up the plane. So first I am considering when it is thrown up the plane. Can you think what difference it makes when it is up the plane and when it is thrown down the plane? Of course, it will make a difference because in both the direction, acceleration will have different components. If it is thrown up the plane, then it will be a retarded motion, and if it is thrown down the plane, it will be an accelerated motion. So, range vary in both the different cases. First, I am considering projectile being thrown up the plane. R max would be, already we have the formula, that is 2u square sin beta cos alpha plus beta upon g cos square alpha. That will be equal to u square upon g 1 plus sin alpha on solving the expression. This will be the final expression for maximum range if projectile is thrown up the plane. Now what if it is thrown down the plane? This time R max will be beta is equal to pi by 4 plus alpha by 2. The condition you can get very easily if you write the equation for the body being projected down the plane, because this time the ax component will be positive. So if you substitute ax to be positive, we will get this condition. You can check in the same manner as we had derived for when it is thrown up the plane. So you will get finally beta is equal to pi by 4 plus alpha by 2. Now if it is substituted in equation, R max would be u square upon g 1 minus sin alpha. Now if we compare these two values, R maximum when it is thrown down the plane and when it is thrown up the plane, then you can see that when it is thrown up the plane, range is lower than when it is thrown down the plane. So of course when it is thrown down the plane, it is an accelerated motion. So range has to be somewhat more than when it is thrown up the plane and it is a retarding motion. So this is how maximum range can be obtained with the help of kinematical equations written along x-axis separately. Let us now come to next term, which is maximum height. Now here there are two ways in which maximum height can be defined. One can be if I am drawing this to be x-axis, this to be y-axis, angle being the same, alpha and beta taken, this is initial projection velocity. Now height can be with respect to inclined plane, then this would be the maximum height which is h. Understood? This is not the vertical height, because when we say height, generally we do mean that it should be the vertical height. Here the maximum height that I have written is height with respect to x-axis, with respect to incline. So when we are writing maximum height with respect to incline, what should be the condition here? We know that for maximum height, if it is in vertical direction, vertical component of velocity should become 0. Similar is the case here. When it is maximum height with respect to the incline, so y component of velocity should become 0. So at this point we can write Vy to be 0. If we now substitute this condition in the equation, Vy square is equal to Uy square plus 2Ay delta y, then Vy has to be 0 if h is the maximum height with respect to incline. So that is 0 is equal to Uy is u square sine square beta minus 2, what is component, y component of acceleration here, g cos alpha, and delta y can be written as h. This is the maximum height we are interested in obtaining. So h will be u square sine square beta upon 2g cos alpha. Again we can compare this result with the maximum height we used to get in projectile motion, which is projected along a horizontal line. So in that one it was uy square upon 2gy. The same result we got here as well. And do remember, if it is asking for maximum vertical height, then this should all be written only in vertical direction. That is the only difference. So if this h has to be along vertical direction, I am writing here vertical, then this will be u vertical and square of it upon 2 g in vertical direction, that will be g itself. So this is how maximum height can be obtained, whether it is with respect to the inclined plane or in vertical direction. One illustration I have chosen for you, in which you will see a number of things we are going to calculate. So how calculations are made if it is for projectile motion along an inclined plane. So here, as you can see, one projectile is projected horizontally from the plane and it is thrown down the plane. And what things are to be calculated? First is how far from the point of projection will the particle strike the plane. The second is time taken by particle to hit the plane, and third, velocity of particle just before it hits the plane. Okay, let us start with the first one. Here, as we can see, if we represent this as x-axis, here if we represent horizontal direction itself as x-axis and vertical direction as y-axis. Now see, you may think that just now I had taken along the incline x-axis and perpendicular to incline as y-axis, and here I am changing my convention. So it can be changed whatever be the condition. So it must be convenient to you. You can take any direction as x-axis and then perpendicular to that direction would be y-axis. Here for convenience, because initial velocity is along horizontal direction, so I have taken axis along the horizontal direction. So now we can write x being in horizontal direction, ux is equal to v and uy is equal to 0. There is no initial vertical component of velocity. It is thrown in horizontal direction. Similarly, since x-axis here is horizontal direction, so ax has to be 0 because the only acceleration is acceleration due to gravity, which is in vertical direction. Ax is 0 and ay is minus of g. As the origin I have taken at a, so at t is equal to 0, we can write x coordinate being 0 and y coordinate also being 0. Now for the entire journey, if it is taking time t, then at time t we can write delta x will be AB cos theta. As you can see, AB is the range along incline, and if we take its x projection, horizontal projection, that would be AB cos theta. Similarly, y position can be written as minus AB sine theta, because origin we had taken at A. Now first it is asking for that when the projectile will strike the plane. So this is asking for value AB. Now we got AB can be written as AB cos theta can be written as VT, as there is no acceleration in horizontal direction. So directly AB cos theta will be equal to VT. And for y-axis, AB sin theta will be, of course, with negative sign because it is coming down from the origin, minus AB sin theta is equal to initial velocity along vertical is 0. Directly it will be half minus g into t square. If we solve these two equations and eliminate t, we will get AB sin theta is equal to g by 2 AB cos theta upon v and square of this, which gives us AB is equal to 2v square sin theta upon g cos square theta, or it can be written as 2v square upon g tan theta into sec theta. So this is the distance travelled along the incline when projectile hits the plane. The second one is time taken by the projectile to hit the plane. The equation we had written already in first part. So t can be written as you can recall, AB cos theta was written as v into t. So from there we can write t directly as AB cos theta upon v. And now AB being known, we can substitute the value, which is 2v square by g tan theta into sec theta. 1 cos theta is already there. These two will be cancelled upon v. 1 v also got cancelled. So it is 2v upon g tan theta. This is the time of flight, we can say. The next is velocity of projectile just before it hits the plane. Okay, so after time t, we have to write what will be its velocity. Again, it can be written in component form. So x component of velocity, if we write vx, it has to be the same as the initial velocity, because in x direction there is no acceleration. So in x direction, velocity has to be same as the initial velocity, which is equal to v. But what about y direction? So vy has to be for this direction. Now we have to write the equation, which is equal to uy plus ayt. As we all know, uy is 0 and ay is minus g. So this is minus g into t. Already we have the value of t. Just substitute it here and that will give 2v upon g tan theta. These two being cancelled, it is equal to minus 2v tan theta. This is y component of velocity after time t, and v is the x component of velocity after time t. On summarizing, we can say that velocity after time t will be, v can be written as square root of vx square plus vy square. So simply square the values we got above, v square plus square of minus 2v tan theta, which gives v square being taken common, it will be 1 plus 4 tan square theta and square root. This is the value of velocity that will be after time t. What about its direction now? As we know, for direction, because velocity will be in this direction, if it is the final velocity, its vertical component being vy, horizontal component being vx. So we can write, if it is making angle beta with x-axis, so tan beta can be written as vy upon vx. Of course, only we are interested in its magnitude. So that will be equal to minus 2v tan theta upon v and its mod. From here we got this is equal to 2 tan theta. So the angle which it is making is with x-axis is tan inverse 2 tan theta. This is how we can solve all the situations which is given in a projectile motion along an inclined plane. In next session, I am going to start one different kind of 2D motion, which is circular motion. Again, that is very popular with the students. So let us see forward to it.